Welcome to our weekly question show. As you can see, we're not outside, we're inside the house because it is pouring rain. We've had non-stop storms here on Vancouver Island. So we're in the set of the Weekly Space Hangout, which is also my office, which is also in the living room of my house. So here we are. All right, as always, wherever you are on my channel, go ahead, ask any question. I will gather them all up and I will answer them here. Let's get started. FrogLungs. Do you think people in the Andromeda galaxy are saying the Milky Way galaxy is hurtling towards them? Absolutely. Well, for starters, I love your avatar. I laugh every time I see it. Absolutely. When you think about it, the mass of Andromeda is far greater than the mass of the Milky Way. So really is not that the Andromeda is coming towards the Milky Way. We are falling into Andromeda. We're the ones that are really being affected the most by this interaction between the Milky Way and Andromeda. And we're going to fall into Andromeda and it's going to tear the Milky Way apart, and then the two galaxies are going to merge together. The supermassive black hole at the heart of the Milky Way is 4.1 million times the mass of the Sun. The supermassive black hole at the heart of Andromeda is 100 million times the mass of the Sun. So Andromeda is a much bigger, more massive galaxy, and it's the one that's really calling the shots here. Daneel Buchner. What's the maximum speed you could achieve using a gravitational slingshot around a black hole? Right, so you're trying to think of a way that you could use black holes to speed up your spacecraft. And before we talk about like black holes, let's talk about for a second how gravitational slingshots work, which is that, when the Voyager spacecrafts or New Horizons used the giant planets in the solar system for a gravity speed boost. You kind of imagine the spacecraft falling into the planet and it picks up velocity, but then as it moves away from the planet, it's being pulled back by the planet, and so that velocity decreases. What the gravitational slingshot does is it lets you take advantage of the orbital momentum of the spacecraft. So for example, Earth is going 30 kilometers per second around the Sun. So if you try to do a gravitational slingshot around the Earth, you would fall into the Earth's gravity well, you'd gain speed, and then you would fly back out, and then you would lose the speed, but you would steal some of that 30 kilometers per second of orbital velocity, and in fact, you would slow the Earth down. So that's kind of how a gravitational slingshot works. It's not about the falling in and falling out. It's about you essentially raising to the orbit of the object that you are chasing. So could you do that with a black hole? Absolutely, right? A black hole is merely a massive object that orbits the center of the Milky Way, just like all the other stars. You could do that with a star, you could do it with a black hole, you could do that with anything. The thing with a black hole is that you could get very close. And so by getting a lot closer than you could with, say, a star, then you could gain more of the black hole's orbital velocity. But the problem is that you try to get close to a black hole and you're going to get torn apart by the tidal forces. You've got this radiation that's coming from the area around the black hole. And if you cross the event horizon, you go in. In theory, it should be possible to go up to relativistic speeds by using multiple black holes, each time stealing more and more orbital velocity. But once you go faster than, say, the black hole is orbiting the center of the Milky Way, they're going to be stealing velocity from you. You're going to be speeding them up. So really, you're not going to be able to use black holes better than you could use any object that you'd be getting in the Milky Way. The problem as well is just the massive amounts of time that are going to happen for you to get from one location around one star to another star. But when you look at how fast the objects are going around the Milky Way, you could, in theory, gain a lot of that velocity by stealing orbital velocity from those objects as you went faster and faster. DocWolph. So could you not have an Earth-sized Trojan planet riding along in a Lagrange point of a sufficiently large main planet, most likely captured there and not in this star system? So the trick with Lagrange points, and again, we've done episodes, people like this topic. The Lagrange point are these 5 stable-ish points that are connected to two objects of mass. So you've got the Sun and you've got the Earth, and that creates 5 Lagrange points. The 3 unstable Lagrange points, the ones that are sort of in line between the Earth and the Sun, and you've got the 2 stable Lagrange points, the ones that are ahead and behind along the orbit. And so the question is, could you have like the sun and like a Jupiter and then have a fairly large planet in one of those stable Lagrange points? The answer is no. You need to have an object that is essentially of insignificant mass compared to the planet. And so an Earth-sized planet, even though it's say 100th the mass of Jupiter, still would be too massive to remain for any period of time in that Lagrange point. You need to have something that is like tiny asteroid sized or spaceship sized or awesome L4 rotating colony sized, but nothing that's the size of a planet. So if you put a planet in there, it would just drift away. SubnetMask. Hey Fraser, what's your day job and what are your hobbies? Who do you live with? What kind of music do you listen to? It's funny to me that there's people who listen to or watch the YouTube videos and they don't know what my day job is. But then there's lots of people that know what my day job is. They don't do it, that I do the YouTube videos. So I am a science and space journalist, and I've been doing that for close to 20 years. When we start this episode, maybe Chad will do it right now. I'm the publisher of Universe Today, which is a space and astronomy news website that I've been running since March of 1999. And for the first 10 years, all I did was report on launches and new images from the Hubble Space Telescope and discoveries in cosmology, and I got to interview astronauts and so on. Then about 10 years ago, I started doing this podcast called Astronomy Cast with Dr. Pamela Gay, who's a PhD astrophysicist. And that's, we've just wrapped up 430 episodes of Astronomy Cast. And then it's only been in the last 4 years that I've been doing these videos here on YouTube. And really it was just that I knew that there was lots of stories that I wanted to be able to tell, lots of concepts that I wanted to be able to get across, that video is the best thing. And so if you go back to the beginning of this Guide to Space series, that is me trying to learn how to do video, coming from a background in print and podcasting. So really my job is I am a science journalist, and what I do here is sort of a tiny part of my larger job, which is I manage the team that reports on all of this space news. What are my hobbies? Video games, mountain biking, traveling, probably in that order. Who do I live with? I have 2 kids, and I have my wife who also operates the camera. And what kind of music? I don't listen to a lot of music. And it's mostly because I really love podcasts. So I like music, but if I'm like walking around or doing work, I'm listening to podcasts just because I love that knowledge so much. And I can't listen to any kind of music while I write and while I do any kind of work. So I have to have sort of silence while I'm writing. And so I don't really get a chance to listen to any music. But while I'm driving the car, my kids are with me, they're playing their music, so I'm kept abreast of all of the music that's coming out these days. So there you go, that's me. Seymour Galley Johnson. Could a redwood tree that's grown on Mars or the Moon get so large that it could be a living building, assuming that the tree is in a building? Redwood trees could almost be buildings right now here on Earth, but right, so the maximum size of a redwood tree, I think it's like 100 meters tall, like 300 plus feet tall, and they're really at the theoretical limit of how large a tree can grow in Earth's gravity and environment. If you built a big enclosed dome on Mars and you grew a tree there, you could definitely get a tree that would get bigger than this limit of how big a tree can get on Earth, because and thanks to the lower gravity. The question is how theoretically big it could get, and the answer is we really don't know until we grow a tree on Mars, because the scale of living things is not only dependent on just how well a tree, for example, can bring water up to its branches while fighting gravity. There could be all kinds of other factors about how well it can pull oxygen or carbon dioxide in from the atmosphere, or how well it can expend it, or what is the possible strength that it can do to hold itself in the soil. So this is one of those things that we're just, we're going to have to go to Mars, we're going to have to plant plants, and we're going to have to see what that lower gravity does to the biology of these these plants and of these crops. And but it would be amazing, right? If the force of gravity on Mars is 1/3 what it is on Earth, can you imagine a tree that is 300 meters tall, that's 1,000 feet, that's as tall as some of the tallest buildings in the world? Imagine one on the moon where it's 1/6. So imagine a tree on the moon that's 600 meters tall. That would be crazy. But really, there just could be so many factors that we don't know what's going to be the one that's going to cause it. Quintin Riekert. Why do you sound so negative about SpaceX? I gave that example. I should have grabbed another one too, where someone's like, why are you gotta be such a SpaceX fanboy? And so this is on a video that we did a couple of weeks ago about SpaceX's new plans with the BFR and how they're gonna be going to Mars by 2024. And it's funny to me that people hear out of me exactly what they wanna hear. So in other words, like what I said was, on the one hand, SpaceX makes rockets land on their launch pads. It is one of the most amazing accomplishments in the history of spaceflight that people have been trying to do for a long time. And the fact that they now do this regularly, it's a routine. We expect it to happen, and now they're using these rockets again. That's, where they land, they can refurbish them, and within a few months, they're able to launch the rocket again. That is an amazing, amazing accomplishment. At the same time, 2024 is only 7 years away, and we've seen enormous delays both with the original Falcon and with the Falcon Heavy, so it's not unreasonable to expect that there will be delays with the BFR. Like, it's just, as Elon Musk himself said, these are aspirational timelines. If everything goes well, then they'll have the BFR flying by 2022 and send the first people to Mars or the first spacecraft to Mars by 2024. But delays happen. There are challenges that come up that will be unforeseen. And so for me, the aspirational timeline is fine, but if it takes an extra 10 years, 20 years, 30, it's fine. It's good to create a completely reusable spacecraft, top and bottom, will change everything and decrease launch costs by a factor that we don't even know what we're going to be able to do. So where do I stand on SpaceX? I am a fanboy, and I am skeptical, and I'm excited, and I'm nervous, and my mind boggles at the potential for what we could do if this kind of things would happen. But I also am not a huge fan of sending human beings to Mars because I think it's kind of dangerous there, and I think there's a lot of challenges that need to be figured out. I have a lot of thoughts about this, but I am definitely neither 100% skeptical or 100% fanboy. I am all those things, and so that's why I find it so funny that people see into my videos almost what they want to see or something. Anyway, so that's all I have to say about that. But I'll keep reporting it because I am incredibly excited about what's going to happen next. But I will also be realistic. Radar Blue. How come the neutron star composed of neutrons has a magnetic field at all? Are neutrons central to magnetism? The neutrons are usually portrayed as no electric charge, unlike the proton and electron. Neutron stars, right, are the remnants left over from supernova explosions, where you got the supernova goes off and then the layers compact down inside, and the protons and the electrons are mashed together into neutrons. And so you've got this ball made of neutrons. But it's not only neutrons, it's mostly made of neutrons, but it's also surrounded by other protons and electrons sort of further out to the outside of it. And so you've got these rotations of this object and these different layers, and that's what leads to these powerful magnetic fields. Silt Strider. Are the planetary planes in our galaxy random, or do they have a tendency to be at a similar angle as our solar system? I modified your question. I think this is what you were asking, that you've got the Milky Way galaxy, and have you got like all kinds of different orientations of solar systems, or are they all kind of lined up like little spinning plates inside this larger spinning plate of the galaxy? And the answer is they're random. They're totally random. They don't match the the plane of the Milky Way itself. And that tells you something about the way these different solar systems formed, right? If the solar systems formed within the galaxy and you got, the galaxy was one, sort of had one axis of rotation, and then all of the solar systems had that same axis of rotation, you would think that they all formed in sort of a chain of events in the way that the planets formed with the sun in our own solar system. Everything is lined up in the plane of the ecliptic. But what we see with the Milky Way is all of these solar systems are arranged completely randomly. And that means that they had a completely separate formation event from the formation of the galaxy itself that they're embedded within. And you can confirm this for yourself. If you go out in the night sky and you're able to know where the sun and the moon pass, I'm pointing sort of where they go compared to my house. You know, for me, the sun rises over there and then heads all the way over there and then kind of sets over there to the west. But the Milky Way sort of starts over there, kind of to the north, and goes across the sky and goes over to the south. And so you can see that they actually form this X. They're not lined up. And that's a way that you can tell for yourself that we don't live lined up with the Milky Way, and in fact, none of the solar systems out there do. Vector Lover 3. I have a question. Given the cost of launching infrastructure, the idea of retiring the ISS, and the idea of a deep space gateway, could we not move and repurpose the ISS? If not to lunar orbit, then only for a one-off mission to Mars. Thanks. I get this question quite a bit, which is like why build new stuff when we've got the International Space Station? And we saw this move, the Valerian and the 1,000 Worlds or something, and they just kept adding to the International Space Station to make a bigger and bigger space station. Eventually they had to move it away from Earth because it was just too close to the gravity well for science reasons. Anyway, I'm not going to debunk that movie, but the point is that so the reason why you don't just keep using the International Space Station, there's a bunch of them, right? One is that the ISS was designed to be close to the magnetic, sort of within the magnetosphere of the Earth. And so it doesn't have the kind of protective shielding that you would want if you're farther away from the Earth than just in low Earth orbit. So that's the first one. So in other words, to make it safer, you would need to up-armor it to be a better protective place. While these new space stations that are being developed and the Orion spacecraft and stuff, they're purpose-built to have the kind of have the kind of radiation shielding that would be better protective when you're away, outside of the magnetosphere. The second thing is that ISS is really massive. It is enormous, it is complicated, it has a lot of moving parts, and to try and move it away from the Earth would actually require a lot of energy to do that. And then the third reason is that it's getting kind of old. I'm just reading this great book called Endurance from Scott Kelly, astronaut Scott Kelly, and he was saying that they now spend a good chunk of their time on the International Space Station just maintaining it. That the various parts that were built back sometimes in the 90s, right? They're still maintaining these parts. Their CO2 scrubbers, their toilets, their water makers, all these things are wearing down, and they're going to get to a point where the amount of time spent maintaining the International Space Station is just too long. So it does make sense to build a purpose-built spacecraft to make a mission to Mars, or a purpose-built spacecraft to be in some kind of lunar orbit. They're expecting that they're going to deorbit the International Space Station by 2028. My guess is they won't. They'll keep extending the lifespan of it, same way that they've been expanding the lifespan of the Hubble Space Telescope, that as long as they can keep getting some science out of it, they're going to keep it going for longer and longer. But it's not the right space station to take to the moon, and definitely not the right space station to take to Mars. Fun for it's true. Hey Fraser, I needed a video on what space actually looks like, but it was mostly concerning false color images. What I'm wondering is what space actually looks like from the naked eye. Say if I teleport in between the orbits of Earth or Mars, or even into interstellar space, and if I open my eyes, what would I see? You would see kind of like what you would see from here on Earth. So in other words, you would see, if you open up your eyes, you would see the Milky Way, you would see bright stars in the sky, you would see bright stars that would be the planets. What you wouldn't see is you wouldn't see sort of the atmospheric shimmering that causes stars. Like every star that you would see would be this perfect pinpoint of light that wouldn't be moving around in the way that they are. But you wouldn't see, like you would still be able to see Andromeda as a sort of hazy, fuzzy bit over there. Like I said, you'd see the Milky Way, you might see some other fuzzy nebulae and things like that, but you wouldn't see those nebulae that we see in the pictures from Hubble Space Telescope. And partly, as I mentioned in that video, that stuff is done with false color, that they take images using 3 separate filters and then they combine the images together and they produce a false color image of what it would look like. But it's just that a camera can record photons for a long period of time. Your eyeballs, your meat cameras, flush out the photons that they receive every couple of seconds. And so you'll never gather enough photons to build up a really pretty picture in your eyes. Even if you were really close, if you moved right beside the Orion Nebula and you looked at it, you wouldn't get this bright, vivid thing with all the colors and all that. You would still just see this sort of fuzzy, hazy bit, and that's all it would look like. Now, if you just took your regular camera, but you could do a really long exposure while you were out in space, then you could produce astrophotographs that looked better than anything anyone can do here on Earth with the same camera. Being outside of the atmosphere of the Earth really helps with just how good of a picture that you can take, but you're still really just limited to the fact that our eyes just can't gather the photons over that long period of time that a telescope can. And so every picture of space that you see is done really using the technology of the camera to produce that image. Another Glenn. Has anyone been developing equipment for processing raw materials in space? We'll need clean water. What about the energy and the chemicals needed for the processes? What will we have to bring with us? What can we use that's already on site? So the term for what you're talking about is called in situ resource utilization. In other words, using the resources of space on site to be able to support your exploration. And this is something that explorers have done forever, right? When you are exploring some new place back in the 1600s or 1500s, you hunted and you gathered food from where you were and you built shelter out of the trees that you cut down, that you didn't bring all that stuff with you. So that concept, that technology makes sense. And so when we go to Mars, for example, we're going to be able to produce methane fuel that's right out of the atmosphere of Mars by pulling in the carbon dioxide atmosphere, mixing it with the hydrogen gained from the water deposits that are on Mars, and being able to produce methane fuel. People are going to be able to use the regolith of Mars to be able to grow crops if that's something that they want. There's going to be all kinds of uses for these materials that are out there. And over time, as our technology, as our ability to 3D print, as our ability to draw in these resources gets better and better and better, you can imagine more and more of the technology used for space being maintained out in space. And the great thing is that out in space, you're already outside of the gravity well of the Earth. Trying to get material from Earth out into space is the worst. But out in space, you're already there. You've got enormous resources. There's metals and water and rock and all the materials that you would need to be able to produce pretty much almost anything. Lots of energy with solar radiation. It's just a matter of building up bit by bit the technologies to be able to do this. Stuniverse. As the sun heats up over these millions of years since Mars' global temperature goes up, would that mean that Mars' state could be a little more comfortable for life? The sun is outputting more radiation, and over time the amount of that radiation is going to be increasing. But the problem is that the sun is also blasting away anything that is any atmosphere that's trying to build up around Mars. And so one of the really cool ideas that I've heard is that you could build this artificial magnetic shield, and you put an L1 Lagrange point in between the sun and Mars, and it sort of acts like a cone that protects Mars itself from the solar radiation that's coming from the sun, and that would actually let the volcanic outgassing build up the strength of the thickness of the Martian atmosphere. And over time, it could warm up and you could get the polar ice caps to melt, and that would thicken up the atmosphere even more. So this is the challenge that you're always going to be faced. The reality is that Mars is dead and it lost its atmosphere a long time ago. And really, unless we get in there and come up with a solution to help rebuild the thickness of that atmosphere, Mars will never really come back. All right, well, another week, another set of your questions. Thank everyone for asking their questions. As always, wherever you are on my channel, just go ahead, just type in your question. It doesn't matter whether it's about the episode or whether it's just some random thought that came into your brain. I'll gather them up and I'll answer them here. I'll see you next week.